Okay, it's 2 minutes after. I think we'll go ahead and get started. Hello, everyone. My name is Kevin Weatherby. I am the VP of Marketing at Auger.AI. I would like to welcome you to another one of our webinar series. Today's presenter is Vlad Kizanov, a machine learning engineer at Auger.AI. We will be discussing how to build optimal machine learning-based prediction models with our tool Auger.AI, which is an automated machine learning service. If you have any questions, please enter them in as we are going along, and we will try to answer them at the end of the webinar. And I'm going to hand it over to Vlad.
Yeah, thanks, Kevin. Hello, everyone. So let's start. Once you want to use Auger.AI, you first need to create a project. Project is a high-level concept which is more related to cluster settings, which will be used to evaluate machine learning tasks. So first, you need to pick up a handy project name, set the number of AWS instances for this project or working nodes, choose the instance type, and set the cluster settings to stable or experimental. So the worker nodes are more related to the deeper search during the optimization and obtaining the faster results, while the instance type is more related to the complexity of the problem you have, like for some complex problems with a large number of features or records, you should pick a larger instance size. Experimental settings contains the newest features. However, be aware that they might be not tested well, so they might not work stable. So once you create a project, you can create several experiments which are related to different data sets or different optimization runs on the same data set. So for each experiment, you also should pick up some name and upload a new data set or choose from uploaded ones. Currently, we support CSV and ARFF data formats, and it's also recommended to use gzip of the data set before uploading to speed up the file, or use a public URL for files approximately larger than 50 megabytes in order to speed up this process. So once the data set is uploaded, you came to the data overview page. So on this page, you can see the data fields, their types, and some other statistics. So first, you need to check out the data type for each field. It's inferred from the data automatically. However, in some cases, it's impossible to infer correct data type, so you should double check it again. Then you can check the feature correlation to get more information about how the data correlates to each other or to the target, and possibly eliminate some features. After this, on the very right, you should check the features you want to use into this experiment and the target you are trying to predict. On the top right corner, you select the problem type and experiment settings. For problem type, currently available classification, regression, and time series. Also, there is a gearbox which related to the options of the current experiment. So for time series, you also need to check the time series data type for the column which is related to the date or time. There are two options for features, periodic and features. This means that features uses the same history as the target, while periodic are features which are known on the prediction time. When you select the time series problem type, there are also some new algorithms added in the experiment options, which are only related to the time series. We'll cover them a bit later. So once you've done with all of things, you should come to experiment settings if you want like to use the default ones and tune them for your particular task. So you should select the number of key faults in cross-validation. The higher number of faults, the more precise the result will be. However, this will take more time. So for some large problems, consider to use low number of faults at first and then use larger number if the results is not stable. Then select appropriate metric for your task. For imbalanced classification tasks, it's recommended to use F1 score. And for a regression task with a lot of outliers, mean absolute error might be more stable than mean squared error. On the bottom, you can select the maximum number of trials to evaluate during this experiment. So this number is kind of trade-off between training time and the final model performance in terms of accuracy or MSE or some other metric you have choose. On the bottom, you can select the advanced options, and then you come to data preprocessing settings. So at first, if your data set contains a lot of categories, you can consider to put lesser number of categorical columns, which will shrink your data set. However, this may reduce the final performance, so use this option carefully. For truly sparse data sets, you can consider larger number of embedded space in order to not throw a lot of sparse columns. And if your data set is very imbalanced, you can use some oversampling algorithm. However, for very imbalanced data set, this might take a lot of time and memory, so please consider to take larger cluster. On the very bottom, there are machine learning algorithms and hyperparameters. So there are default machine learning algorithms are added in a search space. You can see them by a tick in the checkbox, and on the right there is a GR tool which is related to the range of hyperparameters for the current algorithm. So you can modify this for your particular task. For example, support vector classification works well if your dataset contains few samples and many features. Linear algorithms such as linear SVM or logistic regression are suitable for large datasets because they are quite fast, while decision trees usually takes much less memory than gradient boosting methods such as kitty boost, gradient boost, or light GBM, while provide similar performance. And as a general rule, gradient boosting methods shows the best performance. However, they might take some time to optimize the hyperparameters. For each algorithm, the search space also might be modified. However, the default values were obtained by evaluating on a large publicly available dataset and is suboptimal for a wide range of problems. So once you've done with options, you should press Run button on the top right corner, and you'll come up to the leaderboard. The leaderboard shows the top best models together with the hyperparameters and the progress evaluation on the very top. For each model, you can see the metrics, in particular case accuracy, on the very right, and evaluation time spent to train this model. And if you press on the horizontal triple dot, you can see all other metrics calculated with this particular model. Once the evaluation is done, you can check out model options by clicking on the vertical triple dot. There are options related to viewing the model performance and deployed. So if you click on model visualization, you'll come up to the tab where you can see different statistics related to how model feed the data. So for instance, on this particular slide, there are three tabs described. The first one is ROC curve, which shows how good our model at classification in terms of false positives or false negatives. Learning curves shows us whether our model overfit or underfit, and feature importance shows us which features was important during the training and which aren't. And you can consider to run retraining by eliminating the non-important features. Also, there are two ways of deploying the model. The first one is REST API. So once you press the REST API, you should check out the deploy status and wait until it becomes ready, and use the example on the very bottom as an example for making the prediction. Our REST API is based on AWS Lambda, and it has a limit of 3 GB. So please consider Python API for models larger than 3 GB. One other approach is to use Python API. It can be used by downloading the Python package, installing it, and use the code below as an example for making the prediction. This usually faster and more suitable for batch prediction. So please, for more detailed information, check out our documentation at docs.auger.ai.